Thank you very much, and thank you so much for inviting me to come today. I've really enjoyed seeing many of the families here. What I'm going to do is talk about babies. Why would one study babies? For the following reason, I've argued for many years that the only way to understand a phenotypic endpoint at the neural level, at the cognitive level, or at the behavioral level is to trace it back to its developmental origins, because things can start very early that change over developmental time. We know that the infant brain is highly plastic. It's less specialized than the adolescent or the adult brain. And during the infant period, both brain and cognition undergo many, many changes, and there's much more cross-talk across the different regions of the brain than when it becomes highly specialized. So there's a lot of influence of one area to another. This being so, an early deficit in one part of the brain or in one part of cognition might impact other parts of the cognitive system or the neural system over developmental time. And here's an example of that. So we discovered some years ago that in Williams syndrome, there's a real low-level visual problem of making rapid saccadic eye movements, just moving your eyes quickly around an environment. We saw this as leading to atypical gaze following. So when mother or father looks towards an object, the infant with Williams syndrome will be very slow to make that same movement. This can lead to atypical triadic interaction. So we know, for instance, in learning vocabulary, learning language, mother might say bottle, and the baby needs to look where the mother is pointing and where her eye gaze goes very quickly, because she'll come back to the baby and say something else. If that eye movement is very slow, then it's going to impact on vocabulary learning. So what you get is, from a visual deficit of saccadic eye movements, over developmental time, it can affect a verbal output, a verbal learning. So we can see cross-modality effects if we look over developmental time. What I'm going to do very rapidly in the short time I have available is give you some examples of our research on infancy and how we've compared infants with Williams syndrome to infants with other syndromes. The idea being that if you compare to typically developing controls, what we call neurotypicals, you'll get big differences anyway. If you compare across syndromes, quite often you get more subtle clues as to what is causing the deficits. And I'll look at attention, I'll look at number, face processing, and speech processing. So let's first look at a study we did some years ago in attention. And what we did was, we can't point here. If you look at the one at the top, the baby sees a very interesting face in the middle of the screen. Then, say, to the right of the screen, something happens. And then to the left of the screen, something really interesting occurs. And what the baby has to learn over the session is that they should inhibit their eye movements to one side, because it's the opposite side that they'll get a reward, so the cat in this case. So over time, the baby needs to learn to inhibit. And what we found was that the mental age match neurotypical controls learned this very quickly. They quickly learned that even though something is happening here, I look here because that's where I get the reward. When we compared the babies with Williams syndrome and the babies with Fragile X syndrome, we found that both failed, but for different reasons. So the infants and toddlers with Fragile X failed to inhibit. Every time something appeared on one side, their eyes went to it, even though the reward was on the other side. With the babies with Williams syndrome, they stayed fixated in the middle. So they were expected, this nice thing that they got initially stopped them moving their eyes from one side to the other. So we find that looking across the two syndromes, we get a clearer view of what's going on and how they differ. So there are syndrome-specific deficits rather than something general because you have a vulnerable system. Let's now go on to look at number. And here we've started now to use what we call eye tracking. And this is a system whereby the baby is looking at a screen, and we can track by calibrating our system onto their pupils exactly where the baby is looking for how long and what the trajectory of the eye movements are. And you can see it on the left-hand side. I think it comes up on the left. We get a heat map showing us how long the baby looks at each place and where the baby's eyes move from one point to another. And we use this for looking at baby's sensitivity to numerosity, if you like. It isn't counting or anything like that. It's, are they sensitive to changes in number in the environment? And we wanted to know where they originated because we knew that children both with Williams syndrome and Down syndrome have difficulties with number when they get to 5, 6, 7 years of age. So if you watch the screen now and not me, I'll show you the kind of thing that babies see. So they see 2 pairs of objects on each side of the screen. That changes to 2 different objects in different places, different colors, 2 more objects, and after a while, we're expecting babies, if they've understood something about number, to get bored with seeing pairs of objects all the time. And then we change the number on the right-hand side. I hope it's coming up on the right, I can't see. On the right-hand side, we've changed the number to 3. They're less interesting objects, and what we're interested in is, does the baby notice that it's been pairs of objects all along and suddenly the number has changed? And you see this little child leaning over towards the 3 because it's changed. So we did this with objects, and we tested neurotypical infants at 3, 4 months of age, and they can do it fine. And we tested the Williams and Downs infants when they were a little older, at 10 to 39 months of age. And what we found was that the infants with Williams syndrome looked exactly like the neurotypicals. They oriented when the number changed to 3. They were good at it, in other words. The Down syndrome infants looked both sides. They weren't aware of a change in number. We repeated this with dots, and we found the same results. So the Williams look like neurotypicals when they're in infancy, and the Downs look worse. We then went on to look at large number discrimination. This is when you can't look at individual objects, but you're looking at the magnitude that is displayed. And we did this with 8 objects in one session, changing to 16 objects, or 16 objects all the way through, changing to 8 objects. And here the results changed. This time, the infants with Down syndrome looked like the neurotypicals, and the Williams syndrome infants looked both sides equally. They didn't notice the change. So we have 2 differences. For small number, we have the Williams infants looking normal, and for large number, it's the Down syndrome infants. And we wanted to know why. They're both going to end up with problems with number, but are they different? So we hypothesized that maybe this wasn't specific to number as such, but to something more general, like visual attention, visual scanning patterns. We'd seen in those early studies of attention that the Williams syndrome infants stayed very focused in the center of the screen and didn't move their eyes. So we did several experiments that I have no time to tell you about now, but found that infants with Williams syndrome were very impaired in their saccadic eye movements, and we had about 4 different studies showing this. And they also had real problems with visual disengagement, looking away from something that's attracted their attention. By contrast, the infants with Down syndrome were good at making saccadic eye movements. They were a little slower than normal typicals, but neurotypicals, but they moved their eyes when things moved in the environment. But their problem was with sustained attention, keeping on target for a while. They kept moving their eyes around. Oops, what have I done? Oh. So our hypothesis was that maybe when you scan a large array of, say, 16 dots, you need to rapidly move your eyes around. And the Down syndrome infants were good at that. But when you're scanning individual objects, small arrays of 2 or 3 objects, you need to really focus on individual objects. And the Williams syndrome infants were good at that. So we looked at their eye scanning patterns, their eye tracking patterns. And this is a typical pattern of a child with Down syndrome. And you can see the child has moved right across the array, moving its eyes all around the whole array. Whereas the child with Williams syndrome, the infant with Williams syndrome, just moved its eyes around a part of the array, so 3 little objects. And the same with 16, you see the same pattern. The Down syndrome infant doesn't look at all of them, but makes a big eye sweep around the array, whereas the child with Williams syndrome looks at a very specific part. And we argued that this explained the difference between the Williams being so good at small numbers because they could individuate a small number of objects, and the Downs being good at large magnitudes because they swept their eyes around the whole array. And this we really thought was something to do with featural processing. What about face processing? Well, again, we knew a lot about face processing in adults and adolescents with Williams syndrome, but this time we wanted to look at face processing using high-density ERP. And we used, it's like a little hairnet that you put onto the head. It has lots of little sponges on it, and all it does, nothing goes into the baby's head. All it's doing is measuring the electrical activity that comes out of the brain when the baby sees something interesting or hears something interesting. It's really easy to administer to babies. You get fine patterns of temporal activity, and you get a fairly good scalp map of the approximate location, certainly hemispheric differences in terms of location. Why we thought it was important is that very often you can get results that are exactly the same, either across two syndromes or from one syndrome to neurotypical children, in this case, Williams to neurotypical controls, but underlying the behavior are different neural processes. So let me give you an example from the Williams syndrome adults and adolescents, and then I'll come back to the babies. So it's been well known for a long time that certain standardized tests, the Benton, the Rivermead, show that people with Williams syndrome score in the normal range. So they do extremely well, and people have always been very impressed by the face processing abilities. But does that mean that they have an intact face processing module? Are they doing it in the same way as anyone else? And what we looked at was the temporal signatures of this. So we have adolescents and adults wearing these geodesic nets. We're measuring the electrical activity. And we compared human faces, monkey faces, and cars. So 3 pretty different stimuli. And what we found was the following, that although the Williams syndrome had behavioral scores, which were the same as the controls if we looked at these standardized tests, the neural activity was different. So if you look at the top line first, you can see that in the red and blue lines, the human faces and monkey faces show in the controls what we call an N170. So about 170 milliseconds after a face comes on the screen, the brain shows a negative peak. And it takes about the same latency for both as well. But cars look very different, the blue line across the top. The brain is looking at cars in a different way. So it's got a specialized way of processing faces, but a very different way of processing cars. If you now look at the one below it, the Williams syndrome, you see 3 lines that are practically identical. This means that although people with Williams syndrome are good at processing faces, and they really are, they're not doing it in the same specialized way as the neurotypical is. They're showing the same pattern for cars and faces. If we then look at hemispheric differences, if you look this time at the bottom, where the controls are, you'll see that for upright faces, the brain is much more active on the right, in the right hemisphere, and for inverted upside-down faces, it's bilateral activity. And there's a huge statistical difference between upright and inverted faces for controls. If you look at the one above, which are the Williams brains, you see there's actually no difference between the two. For the Williams brain, having a face upright or upside down, the brain goes about that in the same way. Again, suggesting quite clearly featural processing, that what they're doing when they look at faces is much more featural, looking at the individual features in a face, rather than the overall configuration. That should remind you of something about the scanning patterns that we saw with number, one being an overall look at the thing, the other being very close on individual features. So we then looked at this in babies. And if again you look at the screen and not at me, you'll see roughly what the babies see. It's the best I could do on the computer. They see a face, they see another face, another face, another face, and several more. And then they see 2 faces. On the left is the model that they've seen already and should find boring. And on the right, we've changed the eyes, so just a feature. The eyes are a different shape. By contrast, in another part of the study, on the left this time, you see another change, which is the configuration. So each of the features is identical, but we stretched the face, or sometimes we squashed the face, so the configuration changed. And what we found was the following. In the neurotypical, they're much more interested in configural changes, because that's how they normally process faces. They notice features, but configural change is a really important thing. In the Williams, by contrast, it's the featural change that they notice. So when we change the shape of the eyes, they look at it much longer. When we change the configuration, they look at the two equally. And for the Down syndrome group, they showed no difference between the two, still to be probed. But again, it looks like we have, in the Williams syndrome case, featural processing. My final example is from speech processing. I've always been very curious as to why infants with Williams syndrome are really very delayed in the onset of language, the building up of vocabulary, etc. Yet subsequently in development, their language is much better than most other individuals with developmental disorders. It's not perfect, as Stefano was pointing out, but it's certainly impressive compared to other syndromes. And yet early on, we can match individual infants with Down syndrome and Williams syndrome in terms of their vocabulary. So why is language so delayed? And we've looked at many, many things over the years. And I'm just going to mention them because I wanted to keep this very short. We know from work by Musakaka, I think her name is, that they're delayed in the onset of babbling. So most babies start babbling, ba, 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 etc. In Williams syndrome, that is later than in the normal case. They're delayed in segmenting the speech stream. So if you do experiments, which I did with Thierry Nazi from Paris, you can see whether or not the baby is aware of the fact that you put in different parts of speech as they listen to speech, and whether they can break them up. And in Williams syndrome, they're very late in being able to break up the speech stream into separate words. They lack hemispheric specialization. So we did a study where the babies had to reach for things. And if you're lateralized, you usually reach across the center to pick up an object rather than picking it up both sides, because one side is stronger. They lack that specialization early on. They rely more on perceptual cues than linguistic labels. So if you have a series of objects and you give them a label and say, get me another briquet, which is not a word in English, they will look for one that looks like it rather than the one that you've named in a similar way earlier on. In typical development, usually children understand more than they can produce. In Williams syndrome, that imbalance is not there. They tend to sometimes even have better production than understanding, but it's usually quite equal. They don't use or follow eye gaze for referential communication. And this is really interesting because they're very good at dyadic interaction. So they focus on faces and spend a lot of time looking at your face, but they don't follow your face and your eye gaze when you use it to pick out something in the environment. And that, I think, is really important because it shows that there's a real difference between dyadic interaction and the triadic interaction that helps you learn vocabulary and about the world. And often we find that production precedes pointing. In the typical case, the child will go, not naming yet, but pointing at something they like. We've found, several studies now have found that in Williams syndrome, often they will name dog before they point at it, as if they don't understand the referential function of pointing, that it's to share some referential object between. So these are all the reasons why they're held up. But why do they get so much better? And that's the next question we asked with a new study. And this is one, again, we've used the geodesic net to pick out the neural activity. And basically, the problem is as follows, and I'll try and do it. The baby hears something like this. E, So that's a change in vowel from to E. Or they hear I'm not very good at doing it, but they hear a change in pitch. So the baby's sitting there looking at an interesting display, film on the screen, and in the background, they're hearing these sounds. So a standard sound, and occasionally a change of vowel to E, or a change in pitch to a higher And we can pick up, because we can time that exactly to when the brain reacts and find out whether or not they've noticed this. And we matched Williams and Down syndrome on the Mullen, which is an infant baby test of intelligence, to cut a short view. And what we found was the following. In the neurotypical children, they noticed both, but they weren't that interested. They showed some interest, but it was equal. There was no significant difference. In Down syndrome, they reacted much more to the change in pitch from to than to the change in speech sounds. But in Williams syndrome, they were very attentive to the change in speech sounds from to E. So they are paying attention to something that is very relevant subsequently to language. And we think this may be one of the contributors to why they later become so much more proficient than other syndromes in terms of their language development. But what I would like to point out is that we've matched these children on various measures, like the Mullen, like their vocabulary, etc. And the method we've used, taking brain activity, shows us that there are two different pathways going on. The Downs are focused on intonation patterns and sort of general things about language, where the Williams are focused much more on features of language. And we believe that's probably bootstrapping why they eventually get so much better. There are real implications for intervention from everything I've told you, I hope in the time. First of all, they should be syndrome specific. So I've shown you that most of these things are not just general problems that are due to being a vulnerable child because you have a genetic disorder, but they change from Fragile X to Williams to Downs and so forth. Second, I believe they should start early in infancy, and I reiterate what Stefanos said in his talk. That is before, in the case of Williams syndrome, before the number, face, and speech processing strategies actually emerge. So can we get in really early? And not necessarily training in the domain of deficits. So if we take the example of number, I don't think we should be training in number. We should be training in what we've learnt underlies the development of number. So in the Williams case, train saccadic eye movements so that they learn to scan arrays very rapidly. But in the Down syndrome case, train on sustained attention so that they start to individuate objects. And my belief is that if you understand the really low-level underlying processes, you will then get impact not only on number, but on other domains like face processing, speech processing, and so forth. That's the end of my talk, and I just want to make one comment. All of the stuff that I've presented to you is group data. So we've looked at how a group of children with Williams and a group of children with Downs or Fragile X differ. But of course, there are huge individual differences across children. You don't just have Williams syndrome. You get the rest of the genes from mum and dad. So you have a different makeup to the next child with Down syndrome, or Williams syndrome, sorry. Not only that, but the environment plays a huge role. Not only in terms of training, different domains, etc., but the environment will change gene expression. And we've got many studies now from Mike Meany and others showing how the environment can change. We've looked at how the environment, how mother-child interaction, and the style of that interaction will change the milestones, the timing of the milestones. So I'm kind of making a plea now. I think we need to move on to many more studies of individual differences and how the rest of the genome, not just chromosome 7, and the environment play a role in developing children with Williams syndrome. And with that, I'd just like to thank my colleagues and to say in Italian grazie to the Italian Association for inviting me. Thank you.